In this final video, we're just going to go ahead and take a look at how we can utilize MATLAB to be able to find inverse Laplace transforms. And it's actually just as easy to be able to find inverse Laplace as it is regular Laplace in MATLAB. So all we're going to do is we're going to define the function. All right, so let's say we have a function f at s equals 1 over s squared minus 1 squared, or s minus 1 squared, excuse me. We're going to use this function I Laplace, inverse Laplace, f comma t. So we're going to take a function that's in terms of s initially and just turn it into a function of t that's the inverse Laplace. All right. And so let me go ahead and I'll just type that in. So we have sins of t and s. We have our function f is equal to 1 over s minus 1 squared. Right. And then we're going to go ahead and just find I Laplace of f, capital F comma s. It doesn't matter what variable you use, just keep it consistent. We're going to go ahead and execute that. And that's going to give us, oh, I should be in terms of t. So notice it put it back in terms of s, which is okay. It doesn't really matter. But if we want it in terms of t, which we're more accustomed to, we would have t equals, or I'm sorry, the inverse Laplace is t exp of t. And that's pretty cool because that was the problem that we just looked at before. So if I ran this code, I would actually get the 1 over s minus 1 squared. All right, so just to show you how to do this for a little bit more difficult sorts of examples, we have this function. All right, so I'm just going to redefine s, or f, capital F, excuse me. That's going to be 2 over s cubed, or I'm sorry, s squared plus 3, plus quantity s plus 3, divided by s squared plus 4. And finally, s minus 1 divided by s, and so s times quantity s squared plus 9. And close that parenthesis and close that parenthesis. And notice that we can just use the I Laplace function and it's going to go back. So we'll go ahead and execute this. All right, and here's our inverse Laplace transform. Okay, really nicely done for us. Didn't have to do a lot of work, just type it in correctly. All right, so pretty cool. As a second example, let's define a new function g as this animal right here. And if you guys are trying to figure this one out, of course, you would have to go through, do the completing the square in the denominator. You might have to add and subtract the special number on top, and then try to get it to factor out really nicely. So this one's kind of painful if we were to try to do this one by hand, right? But fortunately for us, we have MATLAB, so we're going to have 8 times s plus 3. We're going to divide that by s squared minus 6 times s. Remember, explicit multiplication times 13. I'm going to suppress that. And I'm just going to literally copy and paste this I Laplace function. Instead of f, I'm going to use g, and I'm going to execute it. All right, so here's the first, and then here's the second one. Notice it does all that completing the square for us. All right, really nice of MATLAB to do that. Such a nice person MATLAB is. All right, if I wanted to get it back in terms of another variable, let's just say a for some reason, I would just change that. And as we saw before with the first time, I didn't define that as a symbolic variable. And go ahead and execute that as long as we have a in there. So notice if you really wanted to get it in terms of a different variable, you could, but we're so used to just using t that we'll just execute it that way. All right, so pretty cool that you guys can utilize now MATLAB to be able to find Laplace and inverse Laplace transforms. And then going back to what we did in the first couple of videos, the series solutions of some of these differential equations.